Let's get started. Welcome everyone to a Panasys webinar. This is our webinar called New Requirements and Architectures for the Evolution of HPC Storage. I am Richie Oikawa. I'm our Senior Director of Strategic Marketing, and I am joined by, I am actually joining Curtis Anderson, our software architect. Before I introduce you, let me go over some housekeeping for everyone. Please note that this webinar is being recorded. It will be available for on-demand viewing in a day, let's say a day. I think it usually takes a few hours, but we'll say for a day. We are using the Q&A for actual questions. If you have any issues with the webinar itself or audio, please use the chat, and we have Ela Aurora who will help you for getting things set. She is our program manager for all our webinars and all. With that, Curtis, we're going to go into your presentation, but I was hoping you can give a little more background on yourself, because I think it's really relevant to understanding your perspective of what we see going on and what you see really going on in evolution of HPC storage.
Sure. Yeah, no, it's important to be able to say, well, who's doing this, the speaking? Are they, do they have the background, the street cred, if you will, for what they're saying? So I wrote my first line of software 47 years ago. I've been doing storage related things, software, mostly file systems, but all sorts of different things for 39 years now, 38, I think. So I've done a lot, worked for all the majors. I've been with NetApp and Data Domain, et cetera, et cetera. The project that you will most have heard of is I was one of the original 5 architects on the XFS file system. So I've been with Panasys now for the last 8 years. I did a bunch of HPC work at SGI in the 90s, and then came back around to the HPC market with Panasys. And so been around and done a lot of stuff. So hopefully I've seen enough and can provide some perspective on how we got here and where we're going.
No, I think that's going to be really key when you have questions for all the participants. Please understand that background and the view. This is actually a little different for Panasys in many of our webinars. I will do some just introducing ourselves, but it's really a look at HPC storage, storage and HPC storage from a perspective of someone with this level of background. And I think I think you'll find it very interesting to see that some of the trends and what's going on in looking at the future of HPC storage. But before I turn the mic over to Curtis, I will give you a little more for those who are not familiar with Panasys. I think many of you are, but just quickly, just to let you know, we've been around for over 20, I think we're in our 24th year here. And you'll see this in context of a lot of the things we talk about RAID, but one of the co-inventors of the RAID taxonomy and all was the founder of Panasys, from Dr. Garth Gibson from Carnegie Mellon and all, where a lot of the storage technologies were at the beginning of the millennium was started. We are a pioneer in parallel file systems. You'll hear us talking about PanFS, our parallel file system, and how we instantiate it on our active store appliances. And to the right there, the simplicity, maximize management, that's sort of the whole bread and butter of what Panasys and PanFS was to try to make a complicated parallel file system something that is easy to manage and use for beyond research and labs to commercialization, just the whole gamut of being able to make it easy to be able to run a parallel file system. And the basis of that really is a lot of inherent foundation and the reliability, which Curtis will talk quite a bit about. A large, having been around for over 2 decades, we do cover the gamut of from academia and the research labs, but focus a lot on life sciences, manufacturing, energy, media, and entertainment. And you see the list of the companies that we've worked with and working with in the marketplace. But the key thing that we like to talk about is the 12-year average customer tenure that we have with customers, that when we are able to work with them, that we continue to give them new technology and new products as we move forward. From a product point of view, so the instantiation of PanFS is really across our active store. We have a storage side and a metadata side. And the storage side, we cover, if you look from left to right, a hybrid and all flash, a large capacity, covering the range of capacity, deployment size, and all. And we recently introduced our Ultra Edge product, which is a compact, smaller form factor, really allow us to hit more now the locality, ability to look at remote entry, edge type applications, whether in your primary data center or out to the remote and edge. At the bottom, you'll see our other appliances, the director product of ours, which handles the metadata processing, but also provides the legacy protocol support also for NFS and SMB. We also have, for those who are using InfiniBand as their compute cluster interconnect, we have our router product or gateway product to be able to let you connect to from the InfiniBand to an Ethernet storage backend. PANFS, as we talked about, we look at it as really a suite of software. So we have our portable PANFS that allows us to be able to run it on different platforms. But in addition to that, we surround it with manageability, security, data movement, and data analytics that we go. We have a collaboration with Tempo that allows us to really extend what we provide to the cloud and S3 objects. Have a little drawing here that you'll see later again, but just throw everything in there. What we're able to do and what we'll talk about and what we're understanding is the importance of data management, the visibility and the mobility of that data between ourselves and the cloud, between ourselves and S3, being able to scan all this rapidly. And so we bring this together with a bunch of products. You'll see PAMove and PAMView are product names that we have for that. With that, that's sort of a quick background on Panasis and our products. I'd like to turn this over to Curtis. But actually, before I do that, Curtis, I do want, for those, I did quickly go over those, but on our website, this is a series of webinars that we have. We have product-related webinars. So if you go to our website, you look under resources and webinars, you'll see most recently our announcement on our Ultra Edge product. This is our new product that we announced a couple months ago. We did a webinar on that. You'll see that webinar posted, as well as webinars on our other products like PAMove and PAMView. So please go there and look at the resources if you want more details on the products. And with that, I will turn it over to you, Curtis. So please, we're looking forward to this. Thank you very much.
Certainly. Okay, so the purpose of the talk this morning is to go through sort of where the company Panasis and I think that HPC storage is going to be going. There are sort of macro pressures that are coming from the marketplace. And I mean, everybody's heard about AI and the impact it has, for example. Well, there are others. And so I'm going to go through some of those in this talk. So if you go to the next slide. Okay. So the primary two, and I'll touch it on AI at the very end, but the primary two I wanted to cover is that we've got two major pressures, that the data explosion continues. So lots more data. It used to be terabytes were a big deal. Now petabytes are not really a big deal anymore either. We're talking tens to the big guys have hundreds of petabytes. And the capacity of drives has not increased. So, I mean, a little bit, but, not at the same rate that the overall capacity requirement has increased. And so the number of drives that you have to manage goes up. The scalability of the solution goes up because the drive growth rate isn't keeping up with the total capacity requirements. So that's going on. HPC used to be the sort of ivory tower behind the glass wall. People in lab coats ran it, all sorts of things. Now it's turning into the enterprise core needs this. Be careful of being successful, then all of a sudden people will show up and want you to do things for them. And so what we are seeing is that there is a trend for, as enterprises adopt AI specifically, but HPC technologies in general, they're bringing their expectations. And so it used to be that scratch storage, that was sort of the definition of HPC storage. And it was okay that it went down once a month because it was really fast in between. Well, the enterprises look at that and say, no, that's not okay. So there's another change happening, that productivity. You put a lot of money into your HPC compute cluster. You don't want a storage product being down to make your cluster unproductive. So go to the next slide, please. So how that plays out in practice. The traditional approach is that reliable storage wasn't fast enough to keep up with the HPC cluster. And so we in the community, HPC community, created Scratch, and we differentiated it against Campaign. And Scratch was really super fast, and it was okay that it wasn't reliable because the data wasn't going to live there permanently. It lived permanently on Campaign. You pulled the data files up from Campaign, you computed on them for a while, and then you push the results back. And we used checkpoints to save the state of the calculation if there was a software or hardware fault anywhere in that compute and Scratch space environment, and then we'd restart. Now, but the key observation here is that Scratch storage is made of the same commodity drives as Campaign storage. The drives are all the same. It's a question of how you put them together that makes it Scratch versus Campaign. And the separation proper brought advantages in the past, but it also brings disadvantages that if your working set size is 20% of your Campaign storage size, then you're paying 20% more hardware, at least, probably more because there's a premium for Scratch. Moving data back and forth applies load to Scratch that could be moving data into Scratch, applies load to Scratch that could be used by the compute. It also applies load to Campaign. And so the movement back and forth is costly. You have to over provision for each of them. So you're moving data up from Campaign to Scratch doesn't slow down the Scratch while you're trying to compute on it. You lose the benefit. And you also need something to do the movement for you. You're not just going to use CP or tar. You're going to have a big, large infrastructure that's separately managed from the other two. So you have three products there: Scratch, Campaign, and the movement software, movement structures to manage instead of one. So it served its purpose at the time, but I'm going to make the argument and going to try and convince you, or at least start the conversation about the costs of that and how a single tier architecture can be more efficient and less costly. So next slide.
Right. And rooted in your comment about the size of these storages, it's not just gigabytes of stuff. This is like really large, right? So it's,
oh yes. Oh,
yeah.
Okay. So I'll bring out an analogy that I have used a couple of times that I think is interesting. That you can view data as sort of like water. Small quantities of water are, if you make them steam, they'll go through a pipe very easily, without hardly touching it. If you take your water and leave it as water, then you put some pumps on there and it'll move through the pipes. If, however, the water has turned to ice, then no amount of pushing from a pump is going to move it through your pipes. And you need different architectures to support that. In this case, the analogy is an ice crusher and conveyor belts, very different architecture. So specifically, terabytes or gigabytes are steam, terabytes are water, and petabytes of data are more like ice. Requires different architectures. That'll change over time. That layering will move upward into, I guess, exabytes, whatever beyond petabytes at some point. But that's where we are today. That's the break point in the architectures. Okay, so next slide. There we are. So right, remember that the Campaign and Scratch are both made out of the same commodity drives. And so you end up paying 20, 25, 30% more, depending on how big your working set is compared to your Campaign storage, in raw hardware costs. And then there's the complexity of the multiple layers and the movement software in between, and the fact that you don't have a single namespace. You have two namespaces. You have your Scratch namespace where you have some amount of data that's living there temporarily, and your campaign storage where is the home base for all your data. If you can get to a single tier, you have a single namespace for everything. If you can, so that implies also a single analytics solution, single data movement solution for cloud integration, just everything is simpler if you can get to a single tier. Now, the distinction in the past has been that campaign wasn't fast enough and that Scratch wasn't reliable enough. And so what I'm going to go through now is, okay, how do you get both of those? How can you get a single tier campaign storage, if you will, that is fast enough to support the needs of Scratch? Okay, so let's go to the next, please. So in order to, I'm going to use PanFS as an example to show, a concrete example to show the logic behind this. And so I don't intend this particularly as a, well, actually I do. As sort of an endorsement of PanFS, but the logic behind it still holds true even if you weren't talking about PanFS. But so in the case of PanFS, if you're familiar with it, you've seen this before, that across the bottom are what we call object storage devices, because we are a POSIX file system that's layered over object storage devices. I mean, they're objects. Now, they're not S3 objects, they're T10 SCSI objects. There's some magic there. It's some secret sauce on our part, but they're objects. They have the same kinds of scalability and independence that S3 objects have from each other. At the top, we have a direct flow client. That's the little guy with the, you can see the label there. That knows how to access the object storage devices in parallel. And all of that has a relationship to the directors you see on the left side of your screen that coordinate, that quarterback all of the things that are going on in this picture. Oh, and so this is the traditional structure of a parallel file system. There are many different options. In GPFS, Spectrum Scale is a very different architecture, but Lustre and PanFS have this architecture. It was sort of the original, and then other people are trying different things. The core advantage to a parallel file system over a NetApp or an Isilon or one of those is that you can use the combined performance of all of the OSDs in parallel. That's why it's called parallel file system, in order to get bandwidth going into the compute cluster. So parallel file systems, gigabytes per second to a single file, to a single client, are relatively easy to come by. You want a terabyte per second, we can do that too if you work at it. That's sort of the upper bound of the easy technology path these days, but try to get a terabyte per second out of a traditional enterprise NAS box. That's the reason for a parallel file system and why HPC storage is different than, or it's an example of the argument I made earlier about steam, water, and ice, of how the architectures are different. So let's go to the next slide. Okay, so the distribution that PanFS has across object storage devices leads to some opportunities that we've taken advantage of that aren't straightforward. They're not intuitive, and so I wanted to make sure that it was clear. The reliability of PanFS increases with scale instead of decreases with scale. In normal probability theory of failure domains and things like that, the more devices that have to be operating, the lower your overall reliability. There's a trick to RAID that we also use in PanFS. A 20 wide stripe of RAID hard drives, for example, in the old days when it was first developed, was less reliable than 20 drives on their own. But you add the parity, and what the parity allows you to do is reconstruct the failed drive and then get back to full protection levels. And the reliability of the system is dependent on how quickly you can get that reconstruction done. If it takes a long time, there's higher odds of a second failure happening during that time window. If it happens quickly, there's less odds of a failure, and so the overall reliability of the system is higher. You have to swap out the dead hard drive, but you can do that at your leisure, as long as, and so the key reliability metric there, the key thing that enables reliability of a RAID structure or erasure code, is how quickly you can do recovery. So in the case of PAN-FS, we're doing network erasure coding, a variation of RAID. We support RAID 5 and RAID 6 and a bunch of others. I'll go through that in a minute. We use the combined performance of all of the object storage devices to recover from the failure of any one component. And so that window gets smaller as the scale goes up, because the combined bandwidth of 100 OSDs versus 200 OSDs, 200 is twice as much. And so the window shrinks and the overall system gets more reliable. So that's an example of how the right architecture can give you a system that where the reliability goes up let me back up. In order to make my case that you can effectively use a single tier storage architecture to support both the performance and the reliability of campaign storage, the performance of Scratch, reliability of campaign, you need to have, let's do the analysis and figure out how do I get reliability to go up as the scale goes up. In order to get the performance, you need the scale to go up, but that would normally lead to decreasing reliability. So that's what I'm trying to show here, is that with the right architecture, reliability can go up at the same time as performance is going up. And so that foundation is the key to, can we get there to where we want to be with a single tier architecture? So the only thing I haven't mentioned that's listed on slide here is that the directors are managing all of this. The OSDs, the most of the analysis is about the OSDs and the bandwidth and moving data back and forth during a reconstruction. The directors are organizing all that, orchestrating it. Okay, so let's go to the next slide. Okay, so here's a different aspect of PAN-FS that relates to overall reliability. When you create a file, you can make a decision on any of these characteristics for that file. So I can say I want to rate this file in RAID 5, or I want it in RAID 6. There are different performance and reliability characteristics to the two. We do RAID rebuild, RAID recovery per file rather than per drive. And so although the algorithms are the same as per drive, we're doing it per file. So a RAID 5 file has slightly lower overheads in terms of capacity required and has some different performance characteristics, but it also has slightly lower reliability. RAID 6 has higher reliability, has a very small performance delta to RAID 5. RAID 5 is a little bit better at writes in the middle of a file. RAID 10 is especially much better at writes inside the middle of a file. So you seek out, you do a little overwrite, and then you keep going. You can change the stripe size, meaning that 3 data, 3+2, or 6+2, or up to 20, 25, whatever. There's no particular maximum to that. There are, and so that a wider stripe size will give you higher streaming bandwidth. You're able to apply 6 object storage devices to this one particular file. In aggregate, all the OSDs are all busy because we're going to spread everything randomly across the pool of OSDs, but per file, the stripe size lets you change the bandwidth you can get out of that particular file. Well, you can also change the stripe unit size. So make the amount of data per OSD bigger. And that has interesting consequences for, we store, let me back up. The first, all the little block boxes that are labeled 1 are the first stripe unit. And we, if that's all you have is the first stripe unit, we triple replicate that because for the overheads of a RAID calculation are not wasted, but they're not particularly cost effective on small sizes. So we replicate the data, and then once you graduate to 2, 3, and higher, then it uses the RAID that you have specified. Okay, so it's settable per volume, per directory, or per file, the default. So when you create a new file, it's inherited from one of those. So what I'm trying to show here is that with good architecture, you can include both customer choice and different performance reliability trade-offs at the file level, even though your overall architecture is distributed, shared nothing, scale out. So you have control over it. You can get closer to scratch performance than you would. I mean, the base architecture, RAID 6 is the default. That is very fast, but you can get closer to very high streaming bandwidth with wider stripes, more stripe size of 20, for example, and bigger stripe units. You can get closer to a small random read write IOP, like a database workload, by using RAID 10 on that file, while other files are streaming files that have stripe size 20 and bigger stripe units. So something that's not listed here that's also relevant is that in addition to all of that, we have 4 complete copies of the directory tree. So if in the worst case, if you lose one object storage device for whatever reason, we'll happily rebuild. If you lose 2, we'll happily rebuild. You lose the third one, then you may have actually lost some data. If you lose the third one at the same time, but before we have finished reconstruction on the first 2, if you have a coordinated failure, you lose 3 whole devices at the same time, then we may have lost some data. But because we have a 4th copy of the directory tree, we can tell you precisely, well, we know that all these files are untouched and you don't need to worry about them. They're fine. These are the exact files by full path name that have been affected. And you can, if you have a backup or another source for the data, those are the only ones you need to come back to bring back into the system. It's a different aspect of reliability. Okay, so let's go to the next slide, please.
I don't want to seem like I'm setting this up too much, but the reliability increasing with scale is a complex topic. It's a little counterintuitive. I understand that. This one, in terms of settable per volume, per file, per directory, that's that flexibility, the design up front. It's because it seems to be a key component of being able to do both campaign and scratch and flexibility from upfront design. So yeah.
Yes, the PANFS is fundamentally a software product. We ship it as an appliance because that's much easier for a customer to consume, but the value is all in the software, not particularly in the hardware. And so this is an example of where software can give you different performance reliability trade-offs for and adaptation to different workloads. Like the RAID 10 is going to be much better at a database workload. Normally you wouldn't run a database on an HPC storage system, but if you had to for some reason, then you would use RAID 10 format for that file. So
thanks.
Okay, so I'm going to go through a very specific thing here to show what's possible, why. Okay, we've got all that stuff today. Let's talk about where it could go in the future and why I should believe that, well, maybe this is plausible that I really could use now or in the future a single tier architecture, a single tier storage system for both campaign and scratch. So today, OSDs are shared nothing. One OSD doesn't know anything about any of the other OSDs. Overall reliability depends on per file erasure coding, meaning cross node, cross OSDs. Inside the OSD, we just use RAID 0 today. Simple striping, there's no redundancy inside the OSD. If we were to change that to go to RAID 5 or RAID 6 inside the OSD, then the OSD would fail less often, at least fail from drives. I'll talk about software failures and larger kinds of failures in a second. But the OSD itself could reconstruct it from a failed drive without invoking the cross-node erasure coding. One of the things that does is it allows the OSD to be much larger. If you have if you're only dependent on the cross-node erasure coding recovery, then the time to reconstruct a 500 terabyte OSD is X. If you go to a 4 petabyte OSD, it's going to be 8 times longer, and that longer widens the window and increases your odds of having another failure during that time. If you have RAID within an OSD, then the cross-node erasure coding doesn't even get involved. That node has redundancy. It's rebuilding internally. And so you could have, in theory, all of your nodes rebuilding from simultaneous drive failures all at the same time, and the erasure coding wouldn't get involved. It means you can go to much larger OSDs without affecting reliability or performance. So that reduces cost. Okay, next slide. Okay, so it says do the math. Yeah, well, I have done the math. I won't bore you with the actual spreadsheet. In fact, I couldn't use Excel for this because total nerd thing. Excel it uses internally IEEE floating point numbers, which have a particular amount of resolution that they can give you. And this calculation, 4.8 times 10 to the 36th years. Okay, well, that's a large number, and Excel had rounding errors. It wouldn't give me the right result. I had to fall back on the Unix utility BC to do the calculations for me. So kind of a nerd thing. So this shows you the reliability in mean time to data loss, MTTDL, for PANFS given the RAID 0, 5, or 6 as an internal redundancy within each OSD. RAID 0, the mean time to data loss is 5.5 million years. Now, in practice, that doesn't mean your storage is going to be alive for 5.5 million years. It means that the odds of a failure in the short window called the human lifetime are much lower. If you go to RAID 6, 4.8 times 10 to the 36th. Well, that means that the odds of failure during your lifetime are much, much lower. So that's the message to be taken from this. It actually is it seems easy. Oh, well, let's go from RAID 0 to RAID 5 or RAID 6. And the effect on reliability is tremendous. And the combination of much larger OSDs and a larger number of OSDs means that you can grow the scale of your storage much higher, which ultimately gives you the performance that you would have gotten from Scratch if you had a dedicated Scratch, because Scratch is no different than campaign storage. It's all the same commodity drives underneath. It's a question of how you use them, software architecture. Okay, so let's go to the next slide. I said I was going to touch on AI at the end, and so this is the last slide before we go to Q&A. The data management has been a hot topic for a while, and now provenance is becoming a topic that HPC storage needs to take into account. Okay, so what do I mean by that? The AI community with ChatGPT has realized that where the data comes from that they use to train their large language model, where that comes from matters. Finally their lawyers, like Sarah Silverman, the comedian, sued ChatGPT, the OpenAI people, because they used her book without her permission. And so now they've discovered, oh, provenance, the data that I use, I have to be careful what it is. Do I have license to use it? Who has touched it? Has someone injected bias into that data by tweaking it? Or is there bias already in the data? So like HIPAA for personal health records, where the data came from and what's happened to it since needs to be tracked and managed in order for the new AI use cases to not run afoul of legal protections that other people in the world have. So that's where provenance comes in. And since most of most AI, certainly the large stuff, happens on HPC storage, that means that there's a new requirement coming for HPC storage called provenance. And how we respond to that, that's still an open question, but it's another one of those trends going. So I believe that's the last. We're going to Q&A now. So I'm happy to take questions from anybody on anything.
And let me remind everybody, we are using the Q&A tab on your the web platform. Let's go to that. I see there are some questions. Let me read them to you, Curtis. I think.
Sure, thank you.
There's a question here. I'll read it verbatim. Sitting here wondering how much choice the customer users should have, if it should be limited in some ways if possible, and how it might vary based on trying to support a more desperate set of customers.
The questioner wasn't explicit on what kind of choice they were referring to, but I'll take a guess that it used to be that HPC, people bought a cluster and they ran one thing on it, computational fluid dynamics, and that was it. And today, most people, it's become much more cloud-like, that you have a substrate of compute gear and networking and storage, and you're running dozens to hundreds of different kinds of applications on them, what Panasys calls a mixed workload. And so the interpretation of choice that I think you were referring to is partly that the customer needs to have a storage system that will support lots of different workloads simultaneously. Most of it used to be that hardware storage systems and algorithms in the HPC space were co-designed. The old Fortran jobs were designed to create I/O patterns that the file systems of the day could handle well, because that was overall good efficiency for the system. These days, like the frameworks that were created for AI, PyTorch especially, but TensorFlow to a certain degree, they were created on workstations. OpenFOAM, computational fluid dynamics, was created on a workstation, and those applications don't do anything to optimize their I/O pattern for the scale of an HPC system. So that's part of the reason that Panasys added the capability to PanFS of different layouts per file, so that you could adapt via a small tweak to the PanFS configuration, meaning it set an attribute on a file and it adopts that layout, rather than trying to ask the customers to change their applications to do more efficient I/O. If that didn't answer your question, post a follow-up.
It looks like it. I think we'll follow up here. So thank you, Curtis. Okay. Here's another question. Sure. So aside from provenance, can you characterize the difference between HPC storage needs and AI ML requirements?
Yes. AI is there. There are lots of different models where a model is a particular structure of neural network. We're talking about deep learning here. So different model of neural network, and for the different applications. If you're doing vision related things like picking cancerous cells out of a chest x-ray, that's very different than a large language model or a recommender or lots of other things. And the data type, whether it's an image or a little bit of ASCII text, those are stored in different formats. ASCII text is just a linear file. Images tend to be a separate image per file. Fundamentally, AI requires randomness in order to work correctly. So that means that it is not predictable ahead of time which image file is going to be opened next. It has to vary across runs, and during a run, it has to be unpredictable. If you're reading text from a file, you seek out, you find a line boundary, you pick up the next line and you hand it back. You seek to another random place, you grab a line, hand it back. So that randomness is antithetical to, frankly, to the assumptions that HPC storage made through the majority of its history, but yet it's required. And so to date, how people have addressed that is they simply throw hardware at it. They say, oh, you're doing AI, you need all flash. All flash, 300 terabytes of all flash is affordable. 3 petabytes of flash, you're probably spending an extra couple $1 million on that flash that you could be using on compute or networking, one of the other characteristics. And so that's the best answer we have is AI brings a latency requirement and a huge randomness requirement. Latency to keep the IO has to finish before the GPU runs dry of data and needs the next piece of data. And so, okay.
Let me move. Thank you. Yeah, it's pretty complex and
yeah, I'm going on too much detail.
Integrated, yeah, this whole integrated workloads and stuff too. But here's a question about panifest erasure coding. Can it handle different failure zones like node, rack, etc.?
Yes. So within an OSD, there's no redundancy. And so if anything fails inside the OSD, we count the entire OSD failed. And then the network erasure code comes in. And so we today handle node failure for whatever reason, and we reconstruct what the data that would have been on that OSD into spare space that's spread through the rest of the pool. So that's the reason that we can get fast reconstruction time is all of the nodes are generating the data needed, or we're reading data from them. We're doing the XR calculation, the erasure code P and Q, and we're writing it to all of the resulting nodes, distributed. So we handle node failures. We have not had a need to handle rack level failures yet, but to get to the full vision for campaign can be your scratch. You don't need a second tier. We will want to expand to our data placement algorithms to understand the rack level topology so that we could survive an entire rack outage. You get a whole lot of coordinated failures. A lot of OSDs are going to go down at once. So would have to be a very large system to support that. But yes, we will eventually get there.
Here's perhaps I'm looking at the time.
Yeah.
Left here. Perhaps the last question. I think you set this up, I think, when you were talking about database application, but there's a question about what is the correct storage architecture for database applications? So.
Well, as usual, there's an easy answer, Flash. I mean, Flash is, when it first appeared 15, 20 years ago, whatever it was, everyone in the file system business knew, oh, this is going to change everything. The problem with Flash is not that it won't change everything. The problem is that it's still 5x more expensive than hard drives. And so, if you've got a 3-letter agency budget, sure, go all flash for everything. If you're an enterprise who has a 1 million customer per second transaction requirement, go all flash. If you're anywhere below those levels, then you have to ask the question, is there a product that will meet my needs that's a hybrid that has both flash and flash in it as well as hard drives in it? Panifest does. You can go look for the details of how we do that.
There's one other question I do want to go ahead. Sorry.
No, go ahead.
Okay. So and this is on your last slides and all. Because this whole erasure coding and RAID, where you have erasure coding using RAID implementations. But with respect to RAID, so how much performance do you use when you add the RAID inside of these object storage devices and all?
You won't lose any performance. I'm sorry, there will be a very small delta. Well, actually, there won't. No. There won't. If you're going from RAID 0 to RAID 6 inside an OSD, there are two sources of latency. When data is coming in, what we do is we put the incoming data into an NVDIMM, a storage class memory device. Optane used to be a good device for that, but it does not made anymore. We're waiting for CXL to come along because then NVDIMMs will come back finally. But you put the data in there and then you tell the application, I've got this, keep going. And then you can take your time to take that data, drain it out of NVDIM and put it on the hard drives. During reads, you go to read the data and you don't care about the RAID, you're just going to pull it off the hard drives. The fact that there are multiple hard drives means that your seek time is a little bit longer because you have to seek multiple heads and they're time skewed from each other. But so there's no particular cost because of that NVDIM to using RAID 6. The cost is actually hidden behind the NVDIM.
Okay, I think we've come to the end of our time. Thank you, Curtis.
Thank you.
Colleague, but I certainly learned a lot just listening to presentations. There were a few more questions. We will respond to them individually, just so that if you ask questions that weren't answered, that we will follow up with you. And a reminder that there is this presentation is being recorded and will be available for you on demand. And notice sent out to those who weren't able to attend so they can watch it on demand as well. And please look for us for our next webinar coming up in July, probably in a month's time or so. So thank you all for your attendance, and thank you, Curtis, for sharing this presentation.